Good morning, everyone. Let's look into these study resources for Module 7. This is the load calculations, and this is specifically for the wind loading. Okay, so load calculation, including the estimation of wind loading. Now, what I've done is I've shown, you can see the screen that what are the components of the study resources there. So it studies is starting from Module 7A, load estimation. Then you have permanent actions, dead loads, imposed actions, what we have also done in your previous assignment. Then limit state notes, additional example of loading. Now, these are the things you can have a look. Okay, it's important. And then you go to actually the wind load estimation of the wind load estimation, and then the tutorial. For example, this is an example where how to calculate the line load and all, which you have already done, but still, if you have an issue, feel free to look into these things. Sorry, I'll open that again. So what that means, it actually contains estimation of all the loads. You have live loads, dead loads, permanent actions, live load, imposed actions, and the wind load estimations. Now let's move on with wind loading. No, this one, yeah, that's probably better. I think you can see, yeah. Okay, now, wind load estimation, I'll go to the tutorial and then we'll come into the things as we need. So what I'll do, I'll download these things. Download. Okay, and then the other one, tutorial and the tutorial solution. It's probably not needed if you look at the tutorial solution. Okay, so let's see here. So estimation of wind loading on structures, it is based on AS 1170.2. Now we'll go into the solution, and what I'll do is in the process, I'll explain some of the things. Now the important point to think about is, in this case, we'll be following the standard, because otherwise the estimation of wind loading will be very, complicated, and it is quite involved. There is no question about that compared to dead load and live load estimation. And the other thing is, if you look at the study days also another thing is provided, which is called, you can see this one. So this is because when I'm introduced the new one, that's why this is there. You can feel free, have a look. Now, NCC I have provided also as a link. Earlier, we used to have a building code of Australia, and this has been now changed to NCC, National Construction Code. So feel free to look into that. Now, what that NCC does is, it actually tells you the different. So what that NCC does is, it actually tells you that what are the requirements when you design and construct a building. So this is a very important one to look at. Now, well, some of the parts, as I've said, it is important to explore this kind of thing, because when you do it in practice, then you will see that how this information will be used. It actually tells you, for example, category 1 to category 9 building, what are the requirements. So if you look at, so Robert, you can see this one, right? NCC?
Yeah.
Good, yeah. So feel free to look at this one. You can see it clearly if you look at the left-hand side. Yeah, left-hand side, you see it all talks about the governing document. Section A, structure, fire resistance. So if you click any of this, for example, structure, if you look at, it says that, how we are it is changing. Then specification for a particular, say, cyclonic areas, what to do. So you can see that it is quite involved because it goes to actually, the spec required to design a building. So you can see energy efficiency, special use. So it is worth looking into this one as you go. But we are now looking into more specific one at this point, and then we look into the wind load estimation. I'll look at here, yeah. So now the important point to look at before we move on is that when we analyze any wind actions on structures, why we are so much dependent on the standard? Simply because otherwise you have to analyze. Now, how do you analyze this? This is nothing to do with structures. This is completely comes from where? Comes from CFD, computational fluid dynamics, because this is a fluid mechanics problem. So what people do is, so it's a CFD, so it's a fluid mechanics problem. That means some sort of fluid is flowing over a structure. Now, in this case, the fluid is air. So when air is flowing over the structure, what is exactly happening? So that behavior you can only study in fluid mechanics, not in solid mechanics. So you can see this one in the screen, that flow lines, or you also call the streamlines. So the streamlines are actually flowing over the structure and it is getting obstructed. You can see it is getting obstructed. So if you look at
this one, that, Suresh, on the presentation. Sorry, Suresh.
So you cannot see that, right?
Yeah, I can only still see the building code.
Hold on. So we are looking at the wind actions and its effect on structures. Now, this is important to note that this comes from fluid mechanics. That means a fluid is actually flowing over a structure, and then what is exactly happening to the structure because, or how the structure is getting affected due to this wind actions. So these are basically the flow lines or the streamlines, which is, that represents the flow. Now we can see the red zone here. So this red zone actually means this is where the direct pressure will be applied to the structure. Yeah. So that's the direct pressure, and that's on the windward wall. So we call it as a windward wall. That means the direction, so through which, from which the wind is actually flowing and hitting the structure. That's called the windward side or windward wall in this case. And if you look at the opposite, that's the leeward side. Now, if you look at these blue portions, this is not blue like this. What does it represent? Red, I have talked about the pressure. What is this blue? Why is it shown like that?
Are they just eddies?
Very good. They're actually the eddies or the separation. That's a separation of the boundary layer, So if you have to study, then you have to study fluid mechanics, the boundary layer theory. Yeah, Hermann Sittling, there's a famous book, which I do have. That's a book on how that, the flow changes in the boundary layer. So the question is here, what is happening is, here it is pressure because it is directly hitting a surface. And if you apply Bernoulli's equation, we can easily calculate the pressure. Again, that's second fluid mechanics, Bernoulli's equation. So wind or any fluid is hitting obstruction or some wall, and then all this velocity or the kinetic energy will be converted to the pressure energy, from where you can calculate half rho v square. That's one part. But then what happens is, after then it is flowing over the structure. Over the structure means that means this has to, if the structure shape is like that, that's why the aerodynamics come into play. If the aerodynamics is perfect means the wind, these flow lines, streamlines can follow exactly the pattern, then there is no separation, but it doesn't happen. So what will happen is, it will get separated. That's the separation. So as a result of the separation, you have eddies, you can see that blue, that zone. Yeah, good. And then also there's an increase in the velocity here, because you can see the distance between the streamlines had become reduced, means there's an increase in the velocity, because it is now passing through a smaller area compared to what it was before. That's why I get the increase in velocity there. So you can look at this cross section and that cross section. Okay. So that means we can see the separation of the boundary layer and separation here and the eddies, and then it is again going to the original one. So you can see that the roof, apart from the windward wall, the roof and the leeward wall are all actually subjected to what is called suction. So there is no pressure there. Why does the suction is created? Because of that AD, because of that separation. It is everything is suction. So if you look at the roof, that's why the next figure shows that we have always a suction on roof in this case. That's why the roof gets blown away. If you press down the roof, so then the roof is not going to be blown away. It blows away because of the resin. It is always being pulled out. That's why you can see the suction. That's where the arrow is. So the suction on roof is the problem which causes the roof to be blown away, and that's the major disaster we always find when you have cyclone and tornado. If you look at the things, it is that. And you can see that the windward edge, it has the value of maximum always. Windward edge is very critical where you get the maximum of these effects. You can see this is the actual distribution, pressure on the windward wall. And then air, this all air moving away from surface. So another suction on the other side of the roof. And here is also we have suction on the leeward wall. So you can see all are suction. Now one thing we have not shown here, which is the side also. Okay, so here what we have talked about is windward wall, leeward wall, and the roof. Now what about the sides? Because the wind will also flow through the sides. So what will happen is you can see also the side also there will be separation, side walls. Because again it is not following the path. Because it is not following the path, again there will be separation. So all these side walls also will be subjected to the suction effect. So it's again a suction, okay? Now, the other thing I'll talk about aerodynamics, and that's why if you look at why we talk about the shape of the aeroplane or even, the sports car and all, the idea is that there should have a minimum separation. The idea is to have so that the wind can actually, the flow profile can actually follow the structural profile. Rarely it happens, but we actually we have done as close as possible. Because in this case, you have less separation, and then also you will have minimum drag, because when something flows through the air, in this case it's not flowing, but still you can have a drag for a building if the building is very long. We are not looking at these things here. If imagine a building which is like 20-meter long or 15-meter long, what will happen is if wind flows like that, so you'll have an additional effect of drag. Drag means it is something as if pulling the building. That's the aeroplane and those they actually subjected to, like drag because you are moving with a speed for a certain fluid, you will have the drag. So two types of drags are there. Now that's again all fluid mechanics, so which is also my another interesting area of study. So this fluid mechanics, if you study, then you see the main thing is the pressure drag. So which you see there that what happens. So now if you come here, that means we have now looked at two effects. One is called pressure. That we usually put a positive sign. Positive sign means pressure, and negative sign means negative pressure or suction. Okay, so these are the two things. Now these are the damage scenario, the what is called a figure. Now we can see that why the roofs will be blown away. Now, if you look at this scenario, this actually explains a lot of story. These windows, either they're open or they can be broken into. So that's why, so if you look at the internal pressure calculation, which will come into when we'll solve the problem, these openings will be very, very important. If you think of that it is enclosed or closed in such a way that the wind cannot flow inside, that is all right. But in many cases, what can happen is windows can be open. So that means wind air can flow through. That's one thing. Secondly, it can also be broken, because in the cyclonic region, we are not doing it here, but good to know that in the cyclonic region in Australia, we look at the standard region C and D, there debris can be thrown into the window and it can be broken, because the cyclone can flow anything. So it can flow something and then just broken the window. Once the window gets broken, then that's a different scenario, because this room is enclosed, imagine. Now suddenly this window gets broken. What will happen? So all the wind will come, and then your internal pressure will increase. Once your internal pressure will increase, what is going to do? It is going to push the roof. This is the same thing happening here. So this increase in the internal pressure will also apply some force on the roof as well to push up. And then you have the suction effect already there. So combination of that, it is easy to have the roof gets blown away. Can you see these things? So these openings will be actually very, very important, how they determine the things, like especially the internal pressure. And we'll look into that, but good to know or good to think about that these openings are really, really critical as far as wind flow is concerned, and it can actually cause significant damage. You can see some other things. I'll also tell you another important thing. When it fails, one of the important thing which is one got to think about is the connections. Connection means that, this loop is connected to, purlin, to the bolts and other things. Now, if any of these connections fail, that is very, very problematic. If one or two fails at a critical points, that is enough to create more problems, because then more and more area will be, I mean, to put it this way, if we see the failure of connection at some important points, then this will make things weaker. That means some more connections will eventually fail, and the roof will be gone. Okay. So we are not looking into the connection here. Connection will comes design in the steel design or the type of structure timber, if then you design a timber. But it is important to know that those play an important role in this prevention of this type of damage. So this is all this explanation section on the roof surfaces, which we are talking about here, and then you can see this one, wind damage scenario. This is crucial, okay? And then the side wall also. Again, the wind, you can see, it is while suction, it can actually blows that wall away. You can see this effect here. Okay. So we might think that what suction is doing, but actually suction can also do havoc, just like pressure. Pressure is his problem. Suction can also be equally problematic. You can see this one on the leeward side. It's just gone. So it will just blow this one. Okay, so there are other effects which I was talking about before. You can see the drag I was talking about before. The very long structure or like this will be subjected to this kind of drag, side walls and the roofs. And the other things will be drag on individual members like this. This is a very, very different scenario which we are not looking at here. You know why? Because this individual member, when they're subjected to wind force, then that behavior is very different from what we're looking at here. And we can actually have effects of like vortex shading, for example. Again, these are all fluid mechanics, vortex shading effect, galloping effect. And in fact, I don't know whether you have come across the singing of we call it singing of telephonic wire. The cable sometimes produces this kind of sound when the wind actually flows through them because of this vortex shading and other effects. So vortex shading is there, galloping is there. So there are different effects can happen when you have this kind of things. Now, they can also happen in other situations, but for individual members, yes, they are very crucial. That is like the transmission tower, because in this case, you see, this is why this is different, because this is not an enclosed structure that the wind is flowing around. It is all individual members. So it is very wide, or I'll say porous. I'm not sure the word wide, but porous structures. And then the dynamic effect. Dynamic effect, again, we are not looking at here. Dynamic effect means producing the vibration effect. And that is again crucial, especially for high-riser buildings. I'll share the story of the Sky Tower in Auckland. Now there's a restaurant at 85th floor level, but they had to close the restaurant if the wind intensity or the storm intensity is very, very high. Because in that case, so we'll see that anything on the table will be thrown away, whether it is plate, glass, or something, because of the sway and the vibration it can cause, wind can cause. So these are the important things to note, that can be crucial. Okay, and for high-riser building, it will be even more critical, because you not only get the variation of the wind loading, but you will also see the tremendous effect of vibration there. Okay. Any question on this? So this, what we have talked about, is basically the effect of the wind action. That means what wind can do. Then the next question will come, where are they coming from? They are actually coming from the pressure, suction, or drag that the wind load is actually producing. So for that, we need to estimate the wind load. So we have this wind loading, read this one. This is estimation of the wind loading as per this one. Now, why this slide is important, that which part or for which case you can apply the standard. And then you will see that there will be many scenarios which will fall outside the standards. That means if you don't know how to apply this one or how to apply in a different context or unknown context, very challenging. If you look at here, it says, includes building and structures height less than 200 meters. So 200 meter, if you think of, it will be roughly like maybe 65 to 60, say 65 storied building. Yeah, something like that. So anything which is greater than 65 storied building, you will have problem. That means you have to analyze them separately. So how to analyze them separately? Any thought? If you have to, if you cannot apply the standard, what are you going to do? We cannot design the structure simply because we don't have the standard. Yes, yes, you create the model, very good. CFD analysis one do. And then also we have the wind tunnel. So what we do is we have the wind tunnel, we produce a simple model, and then test it, what exactly is happening, when the wind flows around the structure. Now, we also have options of checking or testing almost full-scale model in the United States. Yeah. But so we have very big structure you can actually put in the wind tunnel and then test it. So we know many things very well, how, that's what I'm saying. This is very involved. This particular case, estimation of the wind load, we are following some standard that is different. But if you have to really go into how to analyzing this, then it is very involved. Yeah. So you can see even the roof spans less than 100 meters. So that means it is greater than, like you can see, no stadium, because stadium is supposed to be very big. So no stadium, that means you have to design it yourself. These buildings are okay, normal high risers and all this, okay. And then additional information for offshore structures beyond 30 kilometers from shore, bridges and transmission towers. Transmission towers are again crucial, as I've said, because this produces some different kind of effects. Okay, bridges also have a problems in some cases which you need to look into, and especially if the bridges have cables and other things, then you have to see. Okay, now and what about the wind actions? It is that nature is distributed, that means derived from pressures. This is important, that acts on complete surfaces. See, pressure means it is per unit area. It's working on the surfaces, and it's an estimated from meteorological models of wind speed for events in a region and estimated aerodynamics of building. You see, aerodynamics is also coming into picture. Now, what happens is, just like fluid, that means hydrology, we have all hydrological data, like, runoff and other things for maybe so many years. Similarly, here also, we have a record of the cyclone and, all sorts of critical events. So we can now see, which is the most critical cyclone or tornado in a certain area. Now, this is always a short-term loading, and it's a 0.2 second peak gust. So you can see peak gust, and then there are these are some of the figures which are familiar to, isn't it? Where you have seen them when people read the weather report, because they come from there. Because these are all like cyclonic, cyclonic eye effect, this eye of the cyclone. And, so what happens is, if you look at the pressure diagram, you'll see low pressure zone, high pressure zones, yeah? And how do they interact with each other? That means wind will always flow from high pressure to low pressure zone, isn't it? And that causes the problem or the cyclone and other things. Now, what is the design strategy? Now, the design strategy is calculate the site wind speed, V site beta. Okay, now with the characteristic at site before considering the building, and then design, from that you derive design wind speed. You see the notations, B side beta. Beta actually means this is the 8 cardinal directions we are talking about. Cardinal direction means north, south, east, west, northwest, all these things. So that comes from the standard, the figure. So look into the standard for that is 1170.2. And site speed, that means if you are constructing a building here at the open field, what is the speed there? That is meteorological data. So if you look at the standard, it is stable. I think it's stable 4.1. It gives you everything like all those side wind speed. And then from that, you derive the design wind speed. Now, when you look at the design wind speed, this in major directions for consideration in building design, and it is V dash theta. So this theta is basically the orientation of the building. So this is something different. So building can have any orientation. It's nothing to do with north, east, south. North, east, south is different. But the building can be oriented in any direction. That's what the theta represents. And then from that, you calculate the design wind pressure P on surfaces, and then calculate wind actions on structural element. So wind from at least 4 orthogonal directions, forces on surfaces or structural elements from wind pressure or suction, friction and drag. You have 2 types of friction and then pressure drag. And then action effects, forces and moments on complete structures. Any question? Very important slide because it tells you what are the strategies of how to design for an wind action. Okay, so these are the steps. Now what I will do is I'll move on to the solution, but then this is important I want to mention here. Now what NCC does is, now we'll look into this one, recurrence intervals for environmental actions. Again, I'll refer to hydrology because you have already come across these things. What does that actually mean is, what is the recurrence interval of any critical cyclone? Is it 200 years, 500 years, 1000 years? So this is the starting point of design. That means number of people using the structure, importance of structure to community, risk to failure in life if failure. So all this will tell you what is the importance level of any structure. Because this importance level of the structure will determine which critical wind event you will design it for. I'll repeat the sentence. That means how important the structure is, depending on we will choose what severe event we will be choosing for ultimate limit state. For example, this one. Now, this is the earlier NCC 2019, but yes, I don't think there's any change. Check that one, but that is this, because this is very standardized. Buildings which are utilized by a large number of people have a higher importance level. Understood? 1, least risk to people. 2, most normal structures. 3, most public one. Now 4 is very important. Essential services or dangerous activities like nuclear power plant, or even this also comes under hospital or stadium or something where people can actually, even take shelter or something in case of any emergency event. So category 4 is critical. 3 mostly will have it. So you will have mostly 2 and 3 category. Now, if you look at this one, the importance level of the structure, then what happens? You see this plot. It says that as the risk increases, annual probability of exceedances increases. For a normal structure, 1:500. That means it will be designed for a structure where the critical cyclone comes in every 500 years. That means for a cyclone that comes in every 500 years, that's why we use the word annual probability of exceedance, 1:500. If you go to large number of people, number 3 or number 4, you can see number 4, post-disaster or hazardous structures, we can have 1:2000. That means we are designing for a critical wind event for ultimate limit state, which comes in every 2000 years. You can think of a big tsunami or those kind of things may come along with that. Okay, so this is an important thing to think about. That means we are estimating or thinking, okay, this is the importance level of the structure. Once you know the importance level of the structure, then you are deciding what is the annual probability of exceedance. Okay. And if you look at the serviceability, it's not that critical. Usually we take in 25 years. Why is it very low for serviceability? Any thought? So why is it so low? Because ultimate limit states are usually very high. They will be designed for critical wind event. Yes. Critical, if you look at hydrology similarly, critical flood event. That's very clear. But here, you see why the serviceability is low. I mean, the annual probability of exceedance is low.
that would relate to, we can accept a certain level of damage as long as the building is structurally sound and protects the occupants.
Good, very good, yes. And the other thing is that, see, the wind, the way it acts is, it is not sitting for very long time and producing a long-term effect or something. It doesn't do that. Just comes and goes. And you can see the 2-second gust effect. So very good, Robert, yes. And then also we'll add this point that it is not sitting something and then, like producing damage continuously. Yes, so this is the thing. And then we'll look into the site wind speed. We'll start from there. Now let's look into the wind load problem now. So you can see that we look at the tutorial now. Question 1, well, you solve this problem, regional wind speed. Depending on, you can see we have given the importance level, because the importance level will tell you what are the regional wind speed you will be, considering there. So if you look at here, okay. You can see there were Brisbane region B1 importance level 3, V1000 is 60 meter per second, for example. If you look at the first, you can say region B1, what is the region coming from? Again, I say this is, look at section 4, all right, section 4. So look at the table. I think we have explained it also for the same problem. No, sorry, it's not 4. So it's table 3.1. I think there's a change there, sorry. So I'll write it here. So use table 3.1. Table 3.1, and then you'll see there's a Australian map is there, which shows that which area is in which region. So there are different regions, A, B, C, D, and C and D are the cyclonic ones, and A, B are the normal ones, but A also have lots of division. I think it's now A1 to A7 now, because this continuously, very difficult to remember because it's continuously getting changed, but A has lots of zones or divisions. Okay, so you can see that the port headland, you see region D. Region D, that's a cyclonic one. So you can see V2000 is 90 meter per second. You have an important structure, means this is too high speed, 90 meter per second. Do not think it with a car speed. That's converted to kilometer per hour. And then see that what actually the speed is. Because it's meter per second, you are thinking, oh, that's, so correlate that, what that speed actually means. Okay, tell me during the break. So Darwin is, again, it is C. Again, you see, these are all cyclonic zones, C, Darwin. So these are the things to look for. And then we will move on to actual problems. So if you look at this problem, let's look at this one. It will clear lots of things. So if you look at here, we says we have this factory building we want to design. The ridge is not vented. Not vented means the ridge you can think of is closed. Closed means no air is passing through there, not vented. One sidewall contains a loading door. So here, this one, okay, loading door. And we have the dimensions are all given, and you can see the internal frames are to be spaced at 5 meter. So the frames, so that's basically the frame. I'm just drawing in one half. We have other half on the other side. That's a total frame, internal frames. And the building is to be located on a flat exposed site region in A2. You see, A0, A1, A2, all regions are there. Terrain category 2. There are no surrounding buildings and no adverse topography, and the orientation of the building has not been finalized. What does that actually mean? The orientation of the building has not been finalized. The direction is not there. What does that actually means? That you have to find out what is the most critical one or the worst effect. Okay, so determine the internal and external pressures for roofs and walls. That is the objective. Now, first step is the calculation of the site wind speed. Now, site wind speed, again, we are looking at this NCC volume 1, table 1.28. Has this building has this importance of level 2, and the annual probability of accidents is 1:500, table B 1.2b. Okay. And the regional wind speed can be obtained as VR 45 meter per second. Okay. Right. And then, because the orientation of the building has not been finalized, we are using most conservative option. That means the highest value, which is for region A2, will be W cardinal direction. That means in the west direction, we have the maximum speed. That's what we are looking into with MD equals 0. That's called the directional factor. Now, what happens is, if you look at this expression here, side beta, the first term is VR. That's the regional wind speed. One can use that, but there are some modifications factors, or we call them multipliers. So you can see different multipliers are added to that. And this multipliers actually ultimate gives you the value, I mean the wind speed. Now this is again the new one has been introduced, climate change multiplier. It was not there before at all. Climate change multiplier, MC, in this case MC is 1, so we don't have to use that. Now MD, as we are talking about, now if you look at the table, we have now the values of MD for all the regions, B, C and D regions. That's for the directional one. Then you have the climate change multiplier, MC. Building is in terrain category 2, and the average roof height is this one. Why the average roof height is this? 5.2, that figure is important because we have 5 meter and 9 meter. Okay, so average of that, 9 plus 5, 7 meter height. And you can use linear interpolation from table 4.1. You calculate MZ cat, which is called the effect of the terrain. That's for the category. CAT means category. Okay. Now we have already said this is terrain category. So looking at the building of the location, you have to determine which terrain category is this. So if you start with the standard, it will have 0, 1, 2, etc. So if I in this context, we look into that. So then it will be some idea I will get. So if you look at here, okay, these regions we have already talked about. Now, these are the cardinal directions, 8 cardinal directions. You'll see here. So terrain, so when you look at, some of the examples are shown here. So if you have exposed and all, okay, open ocean and all, this is 1, like this kind of things, which is shown here. Then you have open scattered obstructions, 1.5 to 5 meter, farmland airports, you have 2. Then you have 3 suburban area, closely spaced obstructions, 3 to 10 meter height. And then you have 4, like Gold Coast, they have shown an example, like urban area, closely spaced obstruction. So we have to choose, or you have to estimate, okay, which terrain category, which terrain it is located. And then you use that value of MZ cat. Okay, using that table. And the other thing which also involved in this case, though this expression doesn't, or this the problem doesn't show this one, is this. Terrain category, you have to analyze this one. This is a very crucial thing. That means what we are saying is that you have to consider 500 meter or 40 H away from the structure to consider the wind profile. It is not 2 meter. Building is here, then 500 meter or 40 H you have to consider the wind profile. Then you can consider what is actually the categories. Now what can happen is, you might find that within this distance, you have different category can happen. Like terrain category 1, terrain category 2 or something, it can happen because it's long distance. So then if that happens, then what will happen is you have to do what is called weighted average and then calculate this one. So this is important. That means you take the value of that MZ cat and then you calculate what is called the weighted average, weighted average, and then you get a value. Now this is another important one. So what we are basically saying is this: if you draw the structure here like this, and then this is a lagged response, that means we will leave 20Z. 20Z we leave out. Why leave out? Because we have said that use lagged response. So 20Z you can leave out, but then we have this distance, max of 500 and or 40H. You have to consider. to estimate that terrain category. If you've forgotten, then it's important to look at that. So the standard, follow the standard. This standard is quite involved. So we are thinking, okay, that this wind is like this. And then if you see that, okay, different, we are getting, this is terrain category 1, this is terrain category 2, for example. Then you use the weighted average to calculate what is the, value of MZ cat. So if you look at here only we have done the linear interpolation here, but we may have to do that as required. So in this case, we have done the linear interpolation from table 4.1. And then there is no shielding or topographical effect. Now these are important. Shielding means, imagine if I have a building which is surrounded by lots of multi-story building, then wind flow will be significantly affected. So then you have full shielding. So whether the shielding is there or not there, depending on this MS, shielding factor, and the topographical effect is where the building is located. Imagine this building is located at a hill or something. So then the wind flow will be very different if it is located on, like flat land with all buildings. So that's why these factors will come into play. Shielding or topographical effect. In this case, we have not said that you don't have to, consider any of this. But if you have to consider them, then you need to look here, shielding multiplier. You can see that how we can, depending on where the building is located, you can have shielding multiplier, and there are ways to calculate that. Have a look at this one. Recording is already there. If you have any doubt, we'll discuss. But I've explained all the process. But good to know, yes, there are this multiplication, this multiplier can have a role to play. So you have to calculate the appropriate value depending on where they are located. And then the next one, so this is all the shielding parameters we are looking at. Then you have the topographical. So you see this one, topographical multipliers. So topographical means, you see this is hill effect. So specific ranges like in New Zealand, you can see we have M. Lee, there's another effect. That's only New Zealand. But in Australia, we have this kind of things, and then this land shape can affect the flow. So we have MH. Okay. So this is the hill shape multiplier. Again, there's an expression there in the standard which you have to use to calculate that, what is that multiplier. So you can see this plot. So if the building is located here, then you need to have all this information to calculate. If you don't have, then you cannot calculate. You need to have all this information, and then yes, you can calculate that topographical factor there. But certainly you could see that because this is sitting on a hill, you can have different effects. Whether this side, that side, wind is blowing from which side, yeah, and where is it located? Imagine if it is located on top, so it will be again another different scenario because it is very exposed then to wind. Okay, so the idea is we have to estimate first all these multipliers, MC, MD, MZ cat, MS, and MT. Once you have estimated them, then you multiply with the regional wind speed and then get the site wind speed. And in this case, as I've said, it is independent. We have taken the maximum, directional speed or the maximum value of MD. Yes, that's fine. So, and that represents the worst case scenario. Now from that, the next step, if you recall, what we're looking at the slide is the design wind speed. So first step is your site wind speed. You can put an arrow. From this one, we're actually calculating the design wind speed. Now the design wind speed is V design theta. As I've said that theta is the orientation of the building. And in this case, it is not finalized. So we'll take the worst case scenario, 42.57. That's V design speed. Now from that, next step is to determine the design wind pressures. Now the design wind pressure this is the expression. Now again, it comes from Bernoulli's equation, half rho V square, half rho is the air, and V square. That's design speed. Times, there are two factors is multiplied, C shape. Again, why is it red? Because it has been changed in the standard. Earlier, we used to have C fig. It has now become C shape. It represents the aerodynamic shape of the building, or how does it affect the things. And C dyn is a dynamic effect. Now, in this case, you can ignore the dynamic effect. You can think that this natural frequency is less than 1 hertz. So C dyne is 1 plus 6.2. So no need to worry about that. But we have to look into detail what is the C shape is. Okay. So now we'll look into how to estimate the external pressures. Now, any question? Any question? Okay, in that case, we can break the recording.